Hi everybody. This video today is going to go over the lesson 2D in the AP workbook. We're talking about different pieces of a system and how those pieces of the system are interacting with each other. So we have a train engine pulling the train with 3 cars. Each car has the mass shown. Suppose the cars are connected by middle bars right here, here, and here, with tensions indicated in the diagram, which is here, F1, F2, F3. The engine accelerates at a rate of 2 meters per second squared, and then assume that the cars travel on bearings with a negligible friction. All right, one thing before we start is, usually when we think of tension, we think of a string or a spring, something like that. It can be something like a rod. Even though it is a rigid object, it still has tension in it. If you can think about it like maybe on a microscopic level, like, the bonds inside there are getting stretched. So that is tension. We are going to use the dots below. So we have 3 different graphs here, or graph paper, so that we can draw a free body diagram. And they tell you some examples of what to include and what not to include in that. Okay, so one thing is they say, which we need to do, is to make sure, we don't have to be, well, you want to make sure, actually, yeah, you do. You want to make sure that your arrows are the relative sizes. So for instance, if this is a 3,000 kilogram car, I tried to make this 6, 1, 2, 3, 4, 5, 6. I might have gone a little bit over. I tried to make it 6 boxes, thinking that if it's 3,000 kilograms, then 6 boxes would work. And so this is my free body diagram, where this is the force of gravity, this is the normal force, and then this is another force that we need to investigate. And so before we go any further, let's go up to the top again. And when we first started this unit, I talked about maybe putting a circle around whatever you're investigating, and that is the big dot of your free body diagram, and then anything that comes into contact is going to be a vector. So something's hitting the wheels here, so that's a vector of gravity, and that vector has to go the opposite way also, so that's your normal force. Now we also do have this other right here, this force. That is F sub 3. So I'm going to put that into my free body diagram as well. Okay, let's go to the next one. The next one is going to ask us about the next car, which is the 2,000 kilogram car. So now we're putting our attention here. Okay, well, once again, if we look at it, it should have gravity because we've got the wheels touching, so it's touching there. And if it's touching there, then it has a force acting upwards. Then it has a force here and a force on the right. And one thing we need to think about is which of those forces is greater. Would F sub 3 be greater, or would F sub 2 be greater? Because when we put that into our free body diagram, we are going to want to indicate which one's greater by the length of the arrows. Well, first of all, if this was 6 and 6 for boxes for the gravity and the normal force, then when I get to this side, I want to make this one 4 and 4. Okay, because this is 2,000, so if each one is 50, then this is 4 and 4. Then the horizontal forces, this F sub 3, which showed up here, is the same F sub 3 that shows up over here. Those 2 vectors are the same length. They're opposite direction because we're focusing on a different item in our system, but they're the same magnitude. Then over on the right-hand side, we have F sub 2. Now, I was discussing a minute ago, should it be longer or shorter? And the answer is it should be longer. And so a couple questions of why should it be longer? Well, one thing is, let's think about, should they be the same size? Okay, well, in the intro paragraph here, it has an acceleration. So it is accelerating. So it's not constant. If it was constant, then those forces would be equal to each other. Since it's not constant, they're not equal to each other. So it is accelerating, and it is accelerating to the right, so it should be larger. That's one reason. There is another reason that we'll get into in a little bit. All right, then our last free body diagram is focusing in on the 1,000 kilogram car. And so I'm focusing my attention here on this car. My force of gravity is smaller because this is 1,000. So this is 1,000, this is 2,000, this is 3,000. So this is smaller, then my normal force is going to go here. On my diagram, I have F sub 2 going to the left, and I have F sub 1 going to the right. my F sub 2 should be the same exact size as this F sub 2. And my F sub 1 should be even larger. Why? Because it's accelerating to the right. And then underneath here, they're asking us to write an equation that relates the forces. So in this case, the only force that we have is F sub 3. And if we think of force as mass times acceleration, then the mass here is 3,000 kilograms. And so we're just going to leave it as, for now, as 3,000 kilograms times A. Similar thing here, but this time we have two horizontal forces. So we could say F sub 2 minus F sub 3, that's our net force. And that's going to be equal to the 2,000 kilogram car times the acceleration. And then the last one here is we have F sub 1 minus F sub 2. We have the mass and the acceleration. Okay, so these are the three different cars. In this next section, we're going to talk about what if we group them together. And so now we're talking about systems, that we're going to group some things together and work with that system kind of as a whole. So we're going to do a similar thing. This first one is the 2,000 kilogram and the 3,000 kilogram car together. And so if I group those in a circle, I can kind of think of that as like a little bubble where those things are together. Of course, I have my force of gravity and my normal force. And I'm calling that F sub G sub 3 and 2. So it's the 3,000 kilogram car and the 2,000 kilogram car. All right, there are no forces acting to the left, but there is a force acting to the right. In this case, that is F sub 2. Okay, so that's what we have for that system. The next one asks us to put together the 2 and the 1. And so once again, I'm going to draw this circle around it to show this is where I need to focus my attention. And of course, I have force of gravity going down, I have force of gravity normal force going up, and I have my F sub 3 to the left, and I have my F sub 1 to the right. This one that's in the middle, I don't really care about because it's within the system. So we're only looking at the ones that are like interacting on the outside of the system. So once again, we have the force of gravity. This time it's the gravity of car number 2 and car number 1. And then we have the normal force from car 2 and car 1. We have this one acting to the left, which is F sub 3. And then we have another force acting the other way, that's F sub 1. And again, we have to think about the relative lengths of these. And again, I would say if the motion is a forward motion to the right, then this one needs to be bigger. It's accelerating to the right. Okay, well, what if we focused on all three of them together? So I'm looking at this whole thing. Again, I will have the force of gravity and I will have the normal force. On the left, there's no force. On the right, there is. Okay, this time, once again, that F sub 1 is the same F sub 1 as was over here. Okay, so that's that. It is accelerating to the right, so that's the net force is to the right. I'm calling this total. So FG total and FN total. That's what I'm talking about here. And those little equations at the bottom, once again, let's think of this is the only one we have here is F sub 2. And we have adding together these two cars, we have 5,000 kilograms times acceleration. Now in this next one, we have F sub 1 minus F sub 3. And that is equal to these two cars together, which is 3,000. And then on this one, this is kind of an important one because it's the whole car all together, the whole train all together. And the whole train all together is really only being pulled by one force. And that is the whole force. So that's the 3 plus the 2 plus the 1. So that's 6,000 times the acceleration. I want to take a minute to talk about F sub 3 and F sub 2. And I want to talk about which one's going to have the greater force or maybe the greater tension and how we're going to decide that. And so when I ask this question to students, sometimes people say that F sub 3 should be greater than F sub 2. And I ask them, why is that? And they say, well, because F sub 3 is pulling this 3,000 kilogram, whereas F sub 2 is pulling this 1,000 kilogram. That's not actually true. That's not actually true. I bring it up because it's a common misconception, but that's not true. Because let's actually look at what's going on here. This cable, like it's pulling, right? How much is it pulling? Well, it's pulling 3,000 kilograms. How much is this one pulling? Is it pulling 1,000 kilograms? No, it's not. It's pulling 5,000 kilograms, right? It has the 2 and the 3 that's pulling along. So this one is actually higher. The force in this one is higher. The tension in this one is higher. Okay, we should now be able to determine what the actual numbers are. And here's the deal. The reason they didn't figure those numbers earlier is because they wanted you to think about it conceptually and not just with a bunch of numbers, because sometimes the numbers get in the way or sometimes the numbers are a shortcut. So if we go back now, though, and look at each of the forces, we know that F equals ma. So here the F1 is pulling all 3 of them. And F2 is only pulling these 2, and F3 is only pulling this one. And it is 2 meters per second squared. And so this is pulling 6,000 kilograms at a rate of 2 meters per second squared. F equals ma is going to tell me that that is 12,000 newtons. The next one, F sub 2, that's just carrying those 2 cars. And so that's 10,000 newtons. And the last one is only carrying the 1 car. And so that's 3,000 kilograms times 2 meters per second squared, and that is 6,000 newtons. One more question is to come up with an argument, like a reason. Can you verbalize a reason? This is a big thing with AP. They want you to be able to, put it into sentences. So without referencing any math or any numbers, just concepts. Explain why F sub 1 is the greatest tension and F sub 3 is the smallest tension, even though F sub 3 is connected to the greatest mass. Okay, we've talked about this. So here are a couple things that you could write down here. You could say because it's accelerating to the right, the net force has to also be to the right. Or you could say because F sub 1, that should be a sub 1, is pulling the weight of all the cars, whereas F sub 3 is only pulling 1 car. And so, therefore, it has less force. Sometimes I think it helps to look at what the answer key says just to see how did they put it into words. They are saying the same thing that we are saying in here, so that's the same thing. Okay, this is for worksheet 2D. We will have another video for worksheet 2E.